Basics of Gait Part 2. In this video series, I will attempt both to simplify and expand on the neuroanatomical underpinnings of gait. This is in no way an exhaustive discussion and is instead designed to break down some of the more complex aspects of neuroanatomy and physiology into a more easily digestible format. In Part 1, we discussed the foundations of human gait and examined some of the very basic fundamentals of human bipedalism. In Part 2, we will break down the two requirements for gait production: equilibrium and locomotion. The rest of the series, including this video, will be a bit more dense than Part 1, but don't let that discourage you. I will still do my best to keep things digestible and straightforward. These are the two requirements for gait production: balance and movement. Seems simple enough, but let's dive deeper and explore how our nervous system achieves these. In order to maintain equilibrium, there are a number of reflexes and reactions that are used to keep us upright depending on the situation. I'll list them here and break them down individually. Likewise, locomotion essentially amounts to starting to walk and continuing to walk. While there is more underneath the hood here too, the majority of this series will be focused on equilibrium and the systems that maintain it. The theme to remember when studying these is that all of them rely on a loop of input, processing, and output. Righting reflexes are required to change positions from seated or lying down to standing. We all feel the weight of the world via gravity at all times, and the vector always points towards the center of the Earth. We are able to change positions smoothly and assume an upright position only when there is a relative up and down with respect to the Earth. The desire to stand is initiated by frontal cortex, and righting reflexes are then triggered by vestibular, proprioceptive, tactile, and visual stimuli, which we will discuss further in Part 3. Okay, so you are standing upright after getting up from a more gravitationally stable position. Now what? Well, assuming you want to continue standing, you need supporting reactions to kick in. These activate contractions of anti-gravity muscles, which primarily include the quadriceps, gastrocnemius and soleus, and multiple muscles of the neck and back. An exhaustive discussion of which individual muscles are involved is outside the scope of this talk. The important concept to recognize here is that standing is not passive. Multiple muscles must work in concert to support an upright position. Supporting reactions take into account various threats to vertical posture. These include normal body sway, voluntary movements of the limbs and trunk, and external perturbations. Ligaments, tendons, and how they connect to bones and muscle helps to prevent excessive swaying. These reactions and the degree to which each group of muscles contracts in relation to each other are modulated by experience. Supporting reactions are coupled with anticipatory postural reflexes to maintain an upright posture. When your arm is lifted, the trunk shifts to maintain balance. When the action is planned, these reflexes are feed-forward in nature, with the postural adjustments planned in anticipation of voluntary movement. Think of lifting an empty suitcase you thought was ready to break the weight limit. You are likely to fling it upwards and your trunk to shift significantly because the adjustments were planned in advance of an expected degree of muscle contraction. On the other hand, if you are walking your dog and they suddenly see a squirrel, you may get a yank on your arm that disrupts your center of balance. The sensory information from the distally perturbed limb allows for truncal muscles to respond to the expected shift. This is an example of feedback-type anticipatory postural reflexes. Anticipatory postural reflexes activate in response to some expected postural perturbation. But when the center of gravity is shifted beyond a certain point, especially in response to an unexpected stimulus, reactive postural responses are required. The earliest responses of this type involve monosynaptic and polysynaptic spinal reflex arcs. Both reflex types can lead to rapid muscle contractions in response to a sensory input and can bypass higher cortical influence. However, there also exist reflex arcs that extend all the way up to the level of the brain and, in fact, up to the level of cortex. These are called long-loop reflexes because information literally has to make a long loop from the source of sensory input to the appropriate muscle output. Distal muscles tend to be more commonly regulated by long loop reflexes, think calves and ankles for our purposes, whereas proximal muscles are more likely to be activated by short spinal reflexes. The full scope of these responses is complex. They are influenced by visual and vestibular stimuli, nature of the support surface, and by experience. With a strong enough stimulus, your center of gravity can shift further than your anticipatory or reactive postural responses can manage. You feel the panic set in, and rescue reactions must kick in to prevent a fall. These occur automatically, but conscious control can be enacted. The most common reaction is stepping, with the goal being to bring the feet back under the offset center of gravity. This is not always possible or the most effective action. When near a precarious edge, for example, the arms often get involved in a classic windmill fashion. As with many of the responses we have discussed, rescue reactions are highly context-dependent. Finally, there are some stimuli that simply shift your center of gravity too far for any of the previous responses to prevent a fall. You're going down one way or another, so the next immediate goal is to prevent as much bodily damage as possible. The most common reaction is to mitigate damage to the head and face by stretching out the arms directly in front of the torso. Of course, this is only effective if the fall is in the forward direction. Once again, the nature and efficiency of these movements can be modulated by experience, and the interplay between reflex arcs and finely tuned cortical influence can lead to such impressive feats as the fall recovery seen here. This concludes part 2. I have linked some key references in the description, so please take a look if you are interested in learning more. Thanks for watching. See you in part 3, where we break down internal postural schemas and the sensory inputs that drive the reflexes we discussed here.